Right now, as you listen to these words, you're hurtling through the cosmos at an unfathomable speed. Not just on a spinning Earth, but on a planet orbiting a star drifting through a galaxy racing away from countless others. The night sky appears static, peaceful, but this is an illusion, a trick of time and distance. The universe is expanding, stretching apart like an infinite cosmic tapestry. Stars and galaxies are moving away from each other at speeds that defy comprehension. Have you ever gazed at the night sky and felt both insignificant and connected? Those distant lights, many are not stars, but entire galaxies. Collections of billions of stars, each potentially harboring planets like our own. Yet they remain forever beyond our reach. And this is not science fiction. See, this is not speculation. And this is the harsh reality of cosmic physics. A reality we'll explore together throughout our journey. A reality that reshapes how we understand our place in the universe. Tonight, as you drift into sleep, we'll examine why interstellar travel within our own galaxy presents formidable challenges. But more significantly, why intergalactic travel, journeying to another galaxy, faces insurmountable barriers. The mathematics are unforgiving, the physics unyielding, the distances beyond comprehension. Even light itself, the fastest entity in our universe, takes millions or billions of years to bridge these cosmic gaps. We humans, with our brief lifespans and fragile bodies, face limitations that no technology can fully overcome. Yet understanding these limitations offers not despair, but clarity, not restriction, but perspective, a deeper appreciation for our cosmic neighborhood. What if our inability to reach other galaxies isn't a limitation, but a feature of cosmic design? What if these unreachable realms serve as a gentle reminder that exploration has boundaries, that knowledge has horizons, that some questions may remain unanswered? Throughout human history, we've overcome seemingly impossible challenges. We've split the atom, decoded DNA, and sent machines beyond our solar system. Yet the laws of physics present boundaries that even our most ambitious dreams cannot transcend. In this documentary, we'll explore the 4 fundamental barriers to intergalactic travel: time, distance, energy, and the expanding universe itself. Each presents challenges that compound upon the others, creating a perfect storm of cosmic impossibility. We'll journey through the history of astronomy, from ancient stargazers to modern cosmologists. We'll examine how our understanding of the universe's scale has evolved, and how each new discovery has further illuminated why crossing between galaxies remains forever beyond our reach. The stars you see tonight are predominantly from our own galaxy, the Milky Way, a vast spiral of stars, gas and dust spanning 100,000 light-years. Yet even this expanse pales in comparison to the void between galaxies, voids millions of light-years wide. Our nearest galactic neighbor, Andromeda, appears as a faint smudge in our night sky. Yet this smudge contains 1 trillion stars and sits 2.5 million light-years away, a distance so vast that light, traveling at 186,000 miles per second, takes millions of years to cross. Consider this perspective. If the Milky Way were reduced to the size of North America, Andromeda would still be as far away as the Moon is from Earth. The scales defy our everyday experience. They challenge our very notion of distance. Yet these cosmic impossibilities need not diminish our wonder. Rather, they enhance it. They frame our existence within precise boundaries. They define the parameters of our cosmic home. Throughout this documentary, we'll avoid false hope and empty speculation. We won't rely on theoretical shortcuts or science fiction workarounds. Instead, we'll face the mathematics and physics directly. We'll examine what we know, what we suspect, and what remains uncertain. By the end of our journey, you'll understand why intergalactic travel remains forever beyond our reach. Not because we lack imagination or ambition, but because the universe itself has established boundaries that no technology can overcome. This isn't a story of limitation. It's a story of cosmic perspective, of finding meaning within the boundaries that define us, of appreciating the vast yet finite cosmic neighborhood we call home. So settle in. Let the gentle reality of cosmic limitation wash over you, and together we'll explore the harsh yet beautiful truth of our place in this vast, expanding universe. A universe of possibilities and impossibilities alike. We'll begin with the basics, the scale of our cosmic neighborhood. We'll then explore the physics of space travel, the limitations of propulsion, the challenges of time, and finally, the ultimate barrier, the accelerating expansion of the universe itself. Let this knowledge not discourage but enlighten you, not restrict but free you. For understanding our cosmic boundaries allows us to better appreciate the extraordinary privilege of existing within them, of being conscious observers in this vast, dynamic cosmos. Chapter 2. Premise and Human Meaning. Why should we care about the impossibility of intergalactic travel? How does this cosmic limitation affect us, here on Earth, in our everyday lives? These questions touch something deep within the human condition, our innate desire to explore, to reach beyond. Throughout history, humans have pushed boundaries. We've crossed oceans, scaled mountains, ventured to the depths of our oceans and the reaches of our atmosphere. Each frontier conquered has revealed new horizons, new challenges to overcome. There's a pattern to human exploration. What once seemed impossible becomes commonplace. Circumnavigating the globe, flying through the air, walking on the moon. Yet intergalactic travel represents a different kind of impossible. Not a technological barrier, but a fundamental one. This distinction matters. It shapes how we understand our place in the cosmos. It defines the scope of human potential, not as limitless, but as precisely bounded by the laws of physics that govern our universe. Consider the psychological impact of knowing certain frontiers will forever remain beyond our reach. Does this knowledge diminish us? Or does it offer a kind of cosmic humility? A perspective that frames our existence within defined parameters. Many find comfort in boundlessness, in the idea that humanity's potential knows no limits. But there's also comfort in boundaries, in understanding the precise dimensions of our cosmic home, in recognizing that we need not reach everywhere to matter. The Voyager spacecraft, now venturing into interstellar space, will never reach another star system within the operational lifetime of humanity. Yet we celebrate this mission as one of our greatest achievements. The journey itself has value regardless of destination. This perspective applies to our galactic limitations as well. The impossibility of reaching Andromeda doesn't diminish the wonder of exploring our own cosmic neighborhood. The Milky Way alone contains hundreds of billions of stars, trillions of planets, countless opportunities for discovery. Perhaps our cosmic limitations serve as a natural boundary for a species still learning to manage its own world. A species that has yet to demonstrate sustained harmony with its own planetary environment. A species still growing into its current cosmic address. Philosopher Alan Watts once suggested that the meaning of life isn't found in the destination, but in the music of the journey. What if our cosmic limitations simply define the boundaries of our particular symphony? What if they provide the structure within which our cosmic music plays? The recognition of cosmic impossibility isn't a surrender, it's an orientation. Not a closing of doors, but a clarification of which doors stand open. It focuses our attention on the vast yet finite realm that is accessible to us. Imagine standing on a cosmic shoreline. Before you lies the ocean of our own galaxy, vast beyond comprehension, yet theoretically navigable. Beyond that ocean are other shores, other galaxies, visible but unreachable. This boundary defines our cosmic domain. Many religious and philosophical traditions have contemplated boundaries and limitations. Buddhism speaks of accepting what cannot be changed. Stoicism advocates focusing only on what lies within our control. These ancient wisdoms find cosmic expression in our galactic limitations. The scientific truth of intergalactic impossibility resonates with these timeless wisdoms. It invites us to focus our attention, our ambition, our wonder on what lies within reach, to explore thoroughly rather than endlessly, to appreciate deeply rather than broadly. For centuries, humans gazed at the stars without knowing what they were. Now we know they are distant suns. For decades, we've gazed at galaxies, knowing we can never reach them. This knowledge doesn't diminish their beauty or significance. There's freedom in acceptance, energy redirected from impossible dreams to achievable wonders. The Milky Way alone would take millions of lifetimes to explore completely. Our cosmic neighborhood offers more than enough mystery to satisfy our species' curiosity. The harsh reality of intergalactic impossibility also raises profound questions about the fate of intelligence in our universe. If all intelligent species are similarly confined to their home galaxies, what does this mean for the development of cosmic civilizations? Perhaps each galaxy represents a separate experiment in evolution and intelligence. Isolated laboratories where life and consciousness can develop along independent trajectories, without interaction, interference, or influence from other galactic civilizations. This cosmic isolation might explain the Fermi paradox, the question of why we haven't encountered other intelligent life. If civilizations are galactically isolated by the same physics that constrains us, the silence of the cosmos becomes more comprehensible. There's poignancy in this cosmic arrangement, each galaxy potentially harboring its own story of evolution, consciousness, and civilization. Each unfolding in isolation, each bounded by the same physical laws, each navigating its own path through cosmic time. As you drift towards sleep, consider that our cosmic limitations need not be viewed as restrictions. They can be seen as definitional. They tell us what kind of beings we are, what kind of universe we inhabit, what kind of future awaits us. Chapter 3: Origins and Early Science. The story of our understanding of galaxies begins long before we knew what galaxies were. Ancient cultures worldwide observed a faint, cloudy band stretching across the night sky. The Greeks called it Galaxius Kuklos, the Milky Circle, giving us the term galaxy. For thousands of years, humans had no concept of other galaxies beyond our own. The Milky Way was thought to encompass the entire universe. Stars, planets, and nebulous clouds all existed within this single cosmic structure. Our cosmic horizon extended no further. This limited perspective wasn't due to lack of observation or curiosity. It stemmed from technological limitations. The unaided human eye can see only so far, can resolve only so much detail, can pierce only so deeply into the cosmic darkness. The first conceptual expansion came in 1610 when Galileo Galilei pointed his primitive telescope toward the Milky Way. What appeared as a diffuse cloud resolved into countless individual stars. The first hint that our cosmic home was more complex than it appeared. Throughout the 1700s, astronomers including Thomas Wright and Immanuel Kant proposed revolutionary ideas. Perhaps the Milky Way was a vast disk of stars. Perhaps the fuzzy nebulae visible through telescopes were actually island universes, separate galaxies like our own. These speculations remained unproven for centuries. The limitations of telescopic technology prevented definitive observations. The true nature of these cosmic structures remained ambiguous. The scale of the universe remained uncertain. Charles Messier, hunting comets in the 18th century, compiled a catalogue of fuzzy objects that might be mistaken for comets. His list, now famous as the Messier catalogue, includes many objects we now know as galaxies. M31, the Andromeda galaxy, was Messier Object 31. Yet Messier had no conception that these objects existed outside our galaxy. To him, they were simply nebulous regions within the Milky Way. The true cosmic scale remained hidden. The universe appeared much smaller than reality. William Herschel attempted the first mapping of the Milky Way in the late 1700s. By counting stars in different directions, he created a rough model of our galaxy. He placed the solar system near the center, an understandable error given his limited data. This geocentric, or rather heliocentric model of the universe persisted well into the 19th century. The cosmos was thought to consist entirely of the Milky Way, a vast but finite collection of stars, with our Sun in a position of cosmic significance. As telescope technology improved through the 19th century, the spiral nebulae became more clearly visible. Astronomers noted their distinctive structure, their similarity to theoretical models of our own galaxy, but their nature remained controversial. The true breakthrough came with a woman whose name deserves to be better known, Henrietta Swan Leavitt. Working at Harvard College Observatory as a computer, a human calculator, she made a discovery that would revolutionize our cosmic understanding. In 1908, Leavitt discovered a relationship between the brightness and pulsation period of certain stars called Cepheid variables. This period luminosity relationship provided astronomers with a cosmic measuring stick, a way to determine vast astronomical distances for the first time. This discovery set the stage for what astronomers call the Great Debate, held in 1920 between Harlow Shapley and Heber Curtis. Their central question: were spiral nebulae distant galaxies or nearby gas clouds within our own Milky Way? Shapley argued that the Milky Way constituted the entire universe. Curtis countered that spiral nebulae were island universes, separate galaxies like our own. The debate remained unresolved, but the answer was coming. The definitive evidence arrived through Edwin Hubble's observations in the 1920s. Using the 100-inch telescope at Mount Wilson Observatory, he identified Cepheid variables in the Andromeda Nebula and calculated its distance using Leavitt's method. His conclusion shattered our cosmic perspective. Andromeda lay far beyond the boundaries of the Milky Way. At approximately 900,000 light-years away, later revised to 2.5 million. It was an entirely separate galaxy. The universe was vastly larger than anyone had imagined. This discovery represented one of the greatest expansions of human perspective in history. Comparable to Copernicus displacing Earth from the center of the solar system, Hubble had displaced our entire galaxy from the center of the universe. The implications were profound. Our cosmic home was just one among countless others. The universe extended far beyond the boundaries of the Milky Way. Our significance in the cosmic hierarchy diminished once again. But Hubble wasn't finished expanding our cosmic perspective. By analyzing the light from distant galaxies, he noticed something strange. Almost all galaxies showed a redshift. Their light stretched toward the red end of the spectrum. This redshift indicated these galaxies were moving away from us. And more surprisingly, the farther the galaxy, the faster it was receding. This relationship, now known as Hubble's law, provided the first evidence of an expanding universe. Chapter 4. First Evidence and Scale. To truly comprehend why intergalactic travel is impossible, we must first understand scale. The distances involved are so vast that our everyday units of measurement become meaningless. Even astronomical units fall short. We must think in terms of light years. A light year represents the distance light travels in 1 year, approximately 5.88 trillion miles or 9.46 trillion kilometers. Light, the fastest entity in our universe, takes an entire year to cover this distance. This becomes our measuring stick for cosmic distances. Let's begin with our cosmic neighborhood. Light from our Sun takes about 8 minutes to reach Earth. Light from Neptune, the outermost major planet, takes about 4 hours. The nearest star beyond our Sun, Proxima Centauri, is 4.25 light-years away. Already we encounter our first barrier to intergalactic travel, interstellar distances within our own galaxy. Using our fastest current spacecraft, it would take roughly 75,000 years to reach Proxima Centauri. A journey spanning thousands of human generations. Our galaxy, the Milky Way, spans approximately 100,000 light-years from edge to edge. If we visualize Earth as a grain of sand, our solar system would be roughly the size of a football field. The Milky Way would be the size of North America. Within this vast cosmic structure, our Sun orbits the galactic center once every 225–250 million years. This galactic year represents the time it takes our entire solar system to make one circuit of the Milky Way. Human civilization has existed for less than 0.01% of this period. Beyond our galaxy lies what astronomers call the local group, a collection of more than 54 galaxies bound together by gravity. The Milky Way and Andromeda are the two largest members. Most others are dwarf galaxies orbiting these giants. The local group spans roughly 10 million light-years, a distance so vast that light traveling at 186,000 miles per second takes 10 million years to cross it. Human civilization has existed for roughly 10,000 years. 1/1000th of this travel time, moving outward, the local group is part of the Virgo supercluster, a collection of galaxy groups and clusters spanning 110 million light-years. This structure contains at least 100 galaxy groups and clusters, and potentially more than 10,000 galaxies. In 2014, astronomers discovered that the Virgo supercluster is just one lobe of an even larger structure, called Laniakea, meaning immense heaven in Hawaiian. This supercluster of superclusters spans 520 million light-years and contains approximately 100,000 galaxies. These structures form along filaments of dark matter, invisible material that makes up roughly 27% of the universe. Visible matter, everything we can see, accounts for just 5%. The remaining 68% is dark energy, which drives the universe's accelerating expansion. This cosmic expansion represents the second major barrier to intergalactic travel. Not only are galaxies incredibly distant, but they're also moving away from each other. And this recession is accelerating over time. creating an ever-widening gulf between cosmic shores. Edwin Hubble's observations in the 1920s first revealed this expansion, but it wasn't until 1998 that astronomers discovered the expansion was accelerating. This finding, which earned a Nobel Prize, fundamentally changed our understanding of cosmic destiny. The implications for intergalactic travel are severe. Galaxies beyond our local group are not only distant, but they're becoming more distant every second. Even if we could travel at near light speed, many galaxies would forever remain beyond our reach. Let's quantify this challenge with an example. The galaxy cluster, MAX J49 plus 2223, sits roughly 5 billion light-years away. If we could somehow travel at 99.99% the speed of light, the journey would take over 5 billion years. But during those 5 billion years, the expanding universe would carry this galaxy cluster even further away. By the time we arrived at its former location, it would have moved billions of light years further. An ever-receding target we could never reach. The mathematics of cosmic expansion reveals a sobering reality. There exists a cosmic horizon, a boundary beyond which objects recede faster than light can travel toward us. Galaxies beyond this horizon can never be reached regardless of our technology. Currently, this cosmic horizon sits approximately 16 to 17 billion light-years away. Galaxies beyond this distance recede faster than light, not because they move through space faster than light, but because the space between us expands so rapidly. This distinction is crucial. While nothing can move through space faster than light, space itself has no such limitation. Space can expand at any rate, carrying distant galaxies away at effective speeds far exceeding light's velocity. The third major barrier to intergalactic travel involves energy requirements. To approach even a fraction of light speed requires enormous energy. Energy that increases exponentially as we approach the cosmic speed limit. According to Einstein's equations, an object with mass requires infinite energy to reach the speed of light. While we might approach 99% or even 99.999% of light speed with sufficient energy, we can never reach or exceed it. Another fundamental cosmic limitation. The final barrier involves time, both cosmic and human. The universe is approximately 13.8 billion years old. Human civilization spans roughly 10,000 years. Our species has existed for about 300,000 years. A cosmic eye blink. Intergalactic journeys would span millions or billions of years. Time frames that exceed not just human lifespans, but potentially the lifespan of our entire species. Even with suspended animation or generational ships, such journeys present insurmountable challenges. As we conclude this first section, consider the night sky differently. Those distant galaxies you see, Andromeda, visible to the naked eye as a faint smudge, the southern pinwheel through telescopes. They represent places we can observe but never touch. They exist as windows, not destinations. As objects of study, not conquest. As reminders of the vast cosmic ocean on whose shores we stand. Looking outward at shores we can see but never reach. In our next section, we'll explore the physics of this limitation in greater detail. We'll examine proposed workarounds like warp drives and wormholes, and we'll confront why even these theoretical shortcuts fail to overcome the harsh reality of cosmic isolation. Chapter 5. Contradictions and Anomalies. As we delve deeper into the cosmic impossibilities of intergalactic travel, we encounter contradictions and anomalies that challenge our understanding. Not contradictions that undermine the fundamental barriers, but nuances that complicate our cosmic perspective. Anomalies that invite deeper examination. The first apparent contradiction involves galaxies themselves. While we've established that the distance between galaxies makes travel between them impossible, the galaxies themselves aren't static objects. They move, interact, and sometimes collide. Our own Milky Way is on a collision course with Andromeda. In approximately 4.5 billion years, these two giant spiral galaxies will begin a cosmic dance that ends in merger. Not a violent collision as the term suggests, but a graceful intermingling of stars and gas clouds. The vast emptiness between stars means few, if any, stellar collisions will occur. This future merger presents an interesting paradox. While we cannot travel to Andromeda, Andromeda is, in a sense, coming to us. The galaxies themselves overcome distances that their inhabitants cannot. A passive form of intergalactic travel driven by gravity's inexorable pull. Yet this doesn't contradict our fundamental premise. The timescale of this galactic merger, billions of years, far exceeds human lifespans or even the likely duration of our civilization. The merger represents a cosmic event we can predict but will never witness. Another anomaly concerns the expanding universe itself. While cosmic expansion accelerates the recession of distant galaxies, this expansion doesn't affect objects bound by gravity. Our local group of galaxies remains gravitationally bound. Its members will not drift apart with cosmic expansion. This creates a complex future scenario. As the universe continues expanding, galaxies beyond our local group will recede faster and faster. Eventually, they'll disappear from view, their light unable to reach us. Future civilizations in our galaxy might observe a night sky containing only local group galaxies. Meanwhile, within our local group, gravity will gradually pull member galaxies together. Over hundreds of billions of years, they may merge into a single, enormous, elliptical galaxy. A cosmic island in an increasingly empty sea, a galaxy with no visible external universe. This scenario represents another form of passive intergalactic travel, not through space, but through time. Not by crossing the void, but by waiting for the void to be bridged. Not through technology, but through gravity and patience. Yet another contradiction emerges when we consider intergalactic objects. Astronomers have detected stars zooming through intergalactic space. These hypervelocity stars, ejected from galaxies by gravitational interactions, travel at millions of miles per hour through the cosmic void. Similarly, some planets may be ejected from their star systems and cast into intergalactic space. These rogue planets, or free-floating planets, travel the void between galaxies. Natural travelers accomplishing what our technology cannot. Even more intriguing are the mysterious fast radio bursts, FRBs, powerful bursts of radio waves lasting just milliseconds. Some originate from other galaxies, traveling billions of light years to reach us. Information crossing intergalactic space even as physical travel remains impossible. But these natural phenomena don't contradict the impossibility of human intergalactic travel, but they do reveal the complexity of cosmic interactions. They remind us that while we cannot cross between galaxies, nature finds ways to bridge these vast distances. Perhaps the most significant anomaly concerns the very nature of space-time itself. Einstein's theory of general relativity describes gravity not as a force, but as curvature in the fabric of space-time. This perspective opens theoretical possibilities for shortcuts across cosmic distances. Physicists have proposed various space-time loopholes that might permit faster-than-light travel. Wormholes connecting distant points in space, warp drives that compress space-time ahead while expanding it behind. Exotic concepts that offer theoretical workarounds to cosmic speed limits. Yet, these theoretical possibilities face severe practical limitations. Wormholes, if they exist naturally, would be microscopically small, unstable, and likely collapse instantly. Creating artificial wormholes would require negative energy, a concept with no proven physical realization. Similarly, warp drives would require exotic matter with negative energy density, material that repels rather than attracts. While quantum mechanics suggests such states might exist briefly at quantum scales, harnessing them for macroscopic effects remains beyond our physics. These theoretical constructs reveal an important distinction between what is physically impossible and what is merely practically impossible, between what violates known physical laws and what simply exceeds our technological capabilities. This distinction matters for our cosmic perspective. Quantum mechanics introduces further anomalies through phenomena like quantum entanglement. Einstein called it spooky action at a distance, particles instantly affecting each other regardless of separation. This suggests connections that transcend conventional space-time. Yet even quantum entanglement cannot transmit useful information faster than light. It creates correlation without communication, connection without contact. Quantum phenomena, while mysterious and counterintuitive, don't provide shortcuts across cosmic distances. Some theoretical physicists propose additional spatial dimensions beyond the three we experience. These extra dimensions, if they exist, might provide shortcuts through space-time, but they remain theoretical constructs with no experimental verification, and accessing them would require energies beyond our technological reach. Another intriguing anomaly emerges from recent observations of galactic motion. The way galaxies move suggests the presence of vast amounts of invisible matter, what astronomers call dark matter. This mysterious substance comprises roughly 27% of the universe. While we can't see dark matter directly, we observe its gravitational effects. It forms vast filaments and webs throughout the cosmos, along which visible matter, stars, gas, and galaxies, accumulates. These structures influence the distribution and movement of galaxies throughout space. Some speculative theories suggest dark matter might interact with normal matter in ways we don't yet understand. Might these interactions someday reveal new physical principles, new approaches to cosmic travel? The honest answer is that we simply don't know. What we do know is that even with our incomplete understanding of cosmic physics, the fundamental barriers to intergalactic travel remain robust. Time, distance, energy requirements, and cosmic expansion present challenges that no known physics can overcome. As we contemplate these anomalies and contradictions, we find not a weakening of our central premise, but a deepening appreciation for cosmic complexity. Not simple answers, but richer questions. Not narrow certainties, but expanding wonder. The universe reveals itself not as a simple system with clear rules, but as a multi-layered reality with interacting forces and principles. What appears impossible from one perspective might appear inevitable from another. What seems fixed in human timescales flows like water in cosmic ones. This complexity invites humility, a recognition that our understanding remains incomplete, that future discoveries may reveal new aspects of reality, yet the fundamental barriers to intergalactic travel remain firmly grounded in our best understanding of physics. Chapter 6. Myths, Misreads, and Edge Cases. Throughout human history, we've created myths to explain what we don't understand. The cosmos has inspired some of our most enduring stories. From ancient creation myths to modern science fiction, our desire to transcend cosmic limitations has spawned its own mythology. The first myth we must address is the technology will save us narrative. The belief that advanced technology will eventually overcome all limitations. including cosmic ones. This perspective often fails to distinguish between engineering problems and fundamental physical constraints. Engineering problems can be solved with sufficient time, resources, and ingenuity. Building faster computers, more efficient engines, stronger materials. But physical constraints represent boundaries set by the universe itself, limits that no technology can transcend. The speed of light in vacuum, approximately 186,282 miles per second, represents one such fundamental limit. Einstein's special relativity established that nothing with mass can reach or exceed this speed. No technological advancement can overcome this barrier. Popular culture often misrepresents this limitation. Science fiction portrays spaceships casually hopping between galaxies, traveling faster than light through hyperspace, subspace, or various fictional dimensions. Creating the impression that such travel awaits future technology, these fictional narratives serve storytelling purposes, not scientific ones. They allow human-scale stories to unfold against cosmic backdrops. They compress vast distances and time frames to human scales, but they misrepresent fundamental physical realities. Another common myth involves the concept of warp speed, the idea that space-time itself can be manipulated to achieve effective faster-than-light travel. While theoretical physics does suggest such possibilities, the practical requirements remain beyond physical realization. Theoretical warp drives like the Alcubierre drive would require exotic matter with negative energy density, material that pushes rather than pulls. While quantum physics suggests such states might exist briefly at quantum scales, sustaining them for macroscopic effects remains physically implausible. Even if such exotic matter could be harnessed, the energy requirements would be staggering. Early calculations suggested energy equivalent to the entire mass of Jupiter converted to pure energy. Later refinements reduced this requirement, but it remains far beyond our technological capabilities. Wormholes represent another staple of science fiction that seems to offer shortcuts across cosmic distances. Theoretical tunnels through space-time connecting distant points. But the physics of wormholes reveals challenges even more formidable than those facing warp drives. Natural wormholes, if they exist at all, would be microscopically small, extremely unstable, and would collapse instantly. Creating and maintaining artificial wormholes would require exotic matter in quantities and configurations that far exceed our technological reach. Even if we could create stable wormholes, traversing them would present additional challenges. Intense tidal forces would tear apart anything entering them. Radiation would be lethal. The very act of passing through might cause the wormhole to collapse. Some misreadings of physics suggest that quantum entanglement might enable faster-than-light communication or even travel. But quantum entanglement cannot transmit usable information faster than light. It creates correlation without causation, connection without communication. The misunderstanding stems from confusing quantum correlation with classical communication. When entangled particles are measured, their states correlate instantly regardless of distance. But extracting meaningful information from this correlation still requires classical communication limited by light speed. Another common misconception involves cryogenic freezing or suspended animation. The idea that humans might be preserved for millennia-long journeys between galaxies. While such technology might someday extend human lifespan, it doesn't overcome the fundamental limitations of intergalactic travel. Even perfectly preserved humans would face the same cosmic barriers: the vast distances, the energy requirements, the expanding universe. Suspended animation addresses only the human lifespan limitation, not the physics of intergalactic travel itself. The generational starship represents another proposed solution: a self-contained ecosystem carrying multiple generations across space. Great-great-great-grandchildren would arrive at destinations their ancestors departed for. But even this approach faces insurmountable challenges for intergalactic journeys. The timeframes involved in intergalactic travel, millions or billions of years, exceed reasonable projections for social stability. No human institution has demonstrated stability over even tens of thousands of years, much less the millions required for intergalactic journeys. Some edge cases seem to offer loopholes to our cosmic limitations. Extremely rare scenarios where stars or planets are ejected from their galaxies at tremendous speeds. If humans happen to live on such objects, they might passively travel between galaxies. But such scenarios represent passive transport, not directed travel. The destinations would be random, the journeys spanning millions of years, and the violent events causing such ejections would likely render any planets uninhabitable. This represents cosmic exile, not exploration. Perhaps the most persistent myth involves alien technology. The belief that advanced extraterrestrial civilizations have overcome these cosmic limitations, that they freely travel between galaxies using physics unknown to us. This represents a modern version of the God of the Gaps argument. While we cannot definitively rule out unknown physics, our current understanding represents centuries of rigorous observation, experimentation, and theoretical work. The burden of proof lies with those proposing violations of established physical principles, not with those upholding them. Some misreadings of astronomy suggest galaxies themselves move faster than light relative to each other. This misunderstands cosmic expansion. Galaxies don't move through space faster than light. Rather, the space between them expands, which can create recession velocities exceeding light speed. This distinction matters because objects cannot move through space faster than light, but space itself has no such limitation. Space can expand at any rate. This expansion doesn't violate relativity, but it does create another barrier to intergalactic travel. Virtual reality and digital consciousness transfer represent more recent proposed workarounds. If human consciousness could be digitized, it might travel between galaxies as information beamed at light speed. This represents information transfer, not physical travel. Even this approach faces limitations. Radio signals weaken with distance, becoming indistinguishable from background noise over intergalactic distances. Directed laser communication might reach farther, but would require precision beyond our current capabilities. And receiving stations would need to exist at the destination. The most profound myth might be our assumption of human continuity, or the belief that humanity as we know it will persist for the cosmic timeframes required for intergalactic ventures. Yet human evolution continues. What emerges after millions of years may bear little resemblance to current humanity. These myths and misreadings reveal something important about human psychology: our tendency to conflate the impractical with the impossible, to assume that sufficient technological advancement can overcome any limitation, to resist accepting fundamental cosmic boundaries. Chapter 7: Stakes and what changes. If true, what are the stakes of accepting our cosmic limitations? How does the impossibility of intergalactic travel shape our understanding of humanity's future? What changes if we embrace rather than resist these limitations? These questions touch something profound about our species' self-conception. For centuries, human progress has been linked to expanding frontiers. Geographic exploration gave way to scientific discovery. Terrestrial boundaries yielded to cosmic ones. Each expansion reinforced our self-image as boundary breakers, limit transcenders, horizon seekers. The impossibility of intergalactic travel presents a different kind of horizon. Not a temporary limitation awaiting technological solution, but a fundamental boundary inherent in cosmic physics. a frontier we can see but never cross, a limit intrinsic to our universe. This realization affects how we conceptualize human destiny. If we cannot spread beyond our galaxy, then our cosmic home has definite, measurable boundaries. Our species' potential expansion, while vast, is not infinite. Our cosmic domain has specific dimensions. Consider the practical implications for long-term human ambition. If the Milky Way represents our cosmic limit, then our focus naturally shifts from endless expansion to sustainable habitation. From conquering ever more distant frontiers to deeply knowing and appreciating our galactic home. The Milky Way contains between 100–400 billion stars. If even a fraction host habitable planets, we face billions of potential worlds to explore. A cosmic neighborhood so vast that even at faster than current speeds, we couldn't visit all its stars in the lifetime of our species. This perspective doesn't diminish human potential. It contextualizes it. It provides a frame for our cosmic aspirations. It defines the playground within which our species' story will unfold. A playground spanning 100,000 light-years, containing billions of potential destinations. If we accept intergalactic impossibility, how might this reshape our cosmic priorities? Perhaps toward deeper rather than broader exploration, toward quality of cosmic experience rather than quantity, toward intensive rather than extensive development of our galactic neighborhood. Our current astronomical efforts already reflect this reality. We design telescopes to observe distant galaxies, not reach them. We develop instruments to detect their light, analyze their composition, understand their dynamics. To know them, not to touch them. The James Webb Space Telescope, humanity's most advanced space observatory, peers across billions of light-years. It observes galaxies as they appeared billions of years ago. It studies their formation and evolution. But it does so through observation, not visitation. This observational relationship with the broader cosmos need not feel limiting. Consider the analogy of astronomy itself. Early astronomers could only observe with naked eyes. Telescopes expanded their vision. Each technological advancement deepened our cosmic connection without requiring physical presence. Perhaps our relationship with other galaxies will follow this pattern. Not physical visitation, but increasingly intimate observation. Not conquest, but comprehension. Not possession, but perception. A relationship based on knowledge rather than presence. The stakes also involve how we measure human achievement. If we define success as overcoming all limitations, then intergalactic impossibility represents failure. But if we define success as flourishing within natural boundaries, then accepting these limitations becomes wisdom, not surrender. Many philosophical traditions emphasize acceptance of natural limitations as the path to fulfillment. Stoicism teaches focusing on what lies within our control. Buddhism advocates accepting impermanence and limitation. Indigenous wisdom traditions emphasize harmony with natural boundaries rather than their conquest. These wisdom traditions find cosmic expression in our galactic limitations. They suggest that meaning comes not from transcending all boundaries, but from flourishing within them. Not from rejecting limits, but from embracing them as defining features of our existence. The stakes extend to how we allocate resources and attention. If intergalactic travel remains forever beyond reach, then massive investments in theoretical, faster-than-light propulsion represent misallocated resources. Efforts better directed toward achievable cosmic goals. These achievable goals might include developing sustainable presence throughout our solar system, exploring nearby star systems, establishing communication networks spanning our galactic neighborhood, deepening our understanding of cosmic processes through observation and theory. Perhaps most significantly, accepting our galactic limitations might foster greater appreciation for Earth itself. If our cosmic expansion has definite boundaries, then our home planet's significance increases rather than diminishes. It remains the known origin point for all future human cosmic endeavors. This perspective might encourage greater planetary stewardship. If Earth represents not just our temporary cradle, but the permanent wellspring of our species, its preservation becomes even more crucial. Not a launching pad to be abandoned, but a foundation to be protected. The stakes also involve time perception. Intergalactic impossibility reminds us that certain processes unfold on timescales beyond human experience. Galaxy mergers spanning billions of years, cosmic expansion measured in trillions, timescales that humble human temporal frameworks. This humbling confrontation with cosmic time can reshape our understanding of urgency and patience. It can contextualize human timeframes within vaster cosmic rhythms. It can teach us to think across generations rather than just within our individual lifespans. What changes if we truly accept these cosmic limitations? Perhaps we develop deeper appreciation for what lies within reach. Perhaps we cultivate cosmic humility alongside cosmic ambition. Perhaps we find meaning in the boundaries that define us as surely as the aspirations that drive us. The question of intergalactic impossibility also raises profound implications for potential extraterrestrial intelligences. If the physics that limits us applies universally, then all technological civilizations throughout the cosmos face similar constraints. All are similarly bounded to their home galaxies. This suggests a universe of isolated galactic civilizations, each developing within its own cosmic island, each observing but never contacting others, each evolving along independent trajectories. An archipelago of intelligence scattered across the cosmic ocean. Such isolation might explain the Fermi paradox, the question of why, given the vastness of the cosmos and the likelihood of other civilizations, we haven't encountered any. If all civilizations are confined to their home galaxies, their absence from ours becomes unsurprising. This perspective transforms how we might conceptualize our cosmic uniqueness or commonality. Perhaps advanced civilizations are common throughout the universe, but eternally isolated from one another, each developing its own solutions to cosmic challenges, each following its own evolutionary path. The philosophical implications extend to questions of purpose. If the cosmos contains numerous isolated civilizations, each bounded to its home galaxy, what does this suggest about cosmic design or meaning? Does isolation serve some function? Do boundaries have purpose? Some might interpret galactic isolation as meaningless, a simple consequence of physics without deeper significance. Others might see purpose in this arrangement. Cosmic laboratories where intelligence can develop independently. Separate experiments in consciousness and civilization. As we approach the conclusion of this section, consider how the harsh reality of intergalactic impossibility might ultimately liberate rather than constrain us. By defining our cosmic boundaries, it focuses our attention. By limiting our reach, it deepens our appreciation. The Milky Way alone contains more worlds than we could explore in millions of years, more resources than we could utilize in billions, more wonder than we could exhaust in trillions. Our galactic home offers near infinite potential within finite boundaries. In our final section, we'll explore how this perspective might shape humanity's long-term relationship with the cosmos, how we might develop a sustainable, meaningful presence throughout our galaxy, how we might come to see the Milky Way not as a limitation, but as our cosmic identity. We'll examine the practical implications for space exploration, telescope development, and communication technologies. We'll consider how accepting our cosmic boundaries might reshape our environmental ethics. And we'll explore how this cosmic perspective might influence human social development over millennia. But first, we must confront the most profound question raised by intergalactic impossibility. If we cannot physically reach other galaxies, how do we establish meaningful relationship with the broader cosmos? How do we connect with what we cannot touch? How do we belong to what we cannot reach? Chapter 8. Strongest Competing Theories. As we approach the culmination of our journey through cosmic limitations, let's examine the strongest competing theories that challenge our premise. Not all scientists agree completely on the absolute impossibility of intergalactic travel. Some propose theoretical frameworks that might, under extremely specific circumstances, offer alternatives. The first serious competing theory involves what physicists call space-time shortcuts. While Einstein's relativity forbids faster-than-light travel through normal space, it doesn't explicitly forbid the creation of shortcuts through the fabric of space-time itself. These theoretical constructs deserve careful examination. Physicist Miguel Alcubierre proposed one such shortcut in 1994. His mathematical model, now known as the Alcubierre drive, describes a bubble of space-time that contracts ahead of a spacecraft while expanding behind it. The ship itself never moves faster than light locally. Within this bubble, space-time itself moves, carrying the spacecraft along like a surfer riding a wave. Since relativity places no speed limit on the expansion or contraction of space itself, this bubble could theoretically travel faster than light relative to distant objects. The mathematics of the Alcubierre drive are consistent with general relativity. But consistency doesn't equal feasibility. The practical requirements reveal why this theoretical possibility remains firmly in the realm of speculation rather than technology. The drive requires what physicists call exotic matter, material with negative energy density. Such material would effectively have negative mass, pushing rather than pulling gravitationally. While quantum physics suggests such states might exist briefly at quantum scales, no known mechanism could produce or sustain them macroscopically. Even if such exotic matter could somehow be produced, the quantities required would be staggering. Early calculations suggested energy equivalent to the entire mass of Jupiter, converted to pure energy. Later refinements reduced this requirement, but it remains far beyond our technological capabilities. A second competing theory involves traversable wormholes, theoretical tunnels through space-time connecting distant points. Unlike black holes, which permit one-way travel toward their center, traversable wormholes would theoretically allow two-way passage, another tantalizing possibility limited by practical constraints. Like the Alcubierre drive, traversable wormholes require exotic matter with negative energy density. They face the same fundamental barrier, the apparent non-existence of stable, macroscopic, negative energy in our universe. A theoretical possibility unsupported by observational evidence. Even if these exotic requirements could somehow be met, additional challenges emerge. Wormholes, if they exist naturally, would be microscopically small. Enlarging them would require amounts of negative energy that increase with size. The energy requirements increase exponentially for human-sized passages. Stability presents another challenge. Natural wormholes would likely be unstable, collapsing instantly. Maintaining stability would require precisely distributed negative energy, and the act of passing through might itself trigger collapse. Theoretical shortcuts remain theoretically treacherous. A third competing theory approaches the problem differently. Rather than attempting to overcome light speed limitations, it proposes working within them. This approach, sometimes called the slow road to the stars, acknowledges cosmic speed limits while seeking to extend human lifespan. Instead, if human consciousness could be digitized or human bodies placed in suspended animation, if spacecraft could reliably function for millions of years, if stable, self-repairing systems could be developed, then perhaps the time barrier rather than the speed barrier might be overcome. This approach faces its own formidable challenges. Consciousness digitization remains hypothetical. Perfect suspended animation unproven. Million-year mechanical reliability unprecedented. And even these advances wouldn't overcome the barrier of cosmic expansion. Distant galaxies would still recede faster than we could approach them. These competing theories, while mathematically intriguing, share a common feature. Each requires physical conditions, materials, or technologies that appear incompatible with our universe as we understand it. Each proposes theoretical possibilities that encounter practical impossibilities. The distinction between theoretical and practical impossibility matters. Theoretical possibilities exist within mathematical models. Practical possibilities must conform to physical reality. The gap between them defines the boundary between speculation and science. This boundary doesn't indicate failure of imagination or ambition. Rather, it reflects the profound insights physics has provided about our universe's fundamental nature. Not arbitrary rules, but intrinsic properties of space, time, matter, and energy. Properties that define our cosmic reality. The search for loopholes continues. Theoretical physicists explore possibilities like cosmic strings, negative energy extraction from quantum vacuums, and higher dimensional shortcuts. Each proposal represents creative engagement with physical laws rather than their rejection. Yet each proposal ultimately encounters the same fundamental barriers: time, distance, energy requirements, and cosmic expansion. These four horsemen of intergalactic impossibility stand guard at the boundary between galaxies, between what we can observe and what we can reach. As we contemplate these competing theories, we must maintain both scientific openness and scientific rigor. We must avoid both premature dismissal of possibilities and premature acceptance of speculations. We must navigate between cosmic pessimism and cosmic fantasy. The strongest competing theories don't promise imminent breakthrough. They don't suggest technology will soon overcome cosmic limitations. Rather, they represent ongoing dialogue between imagination and evidence. Between what we can envision and what we can verify, this tension between theoretical possibility and practical limitation defines the frontier of human knowledge. It invites continued exploration, continued questioning, continued wonder. Not to transcend cosmic boundaries, but to understand them more deeply. Chapter 9. New Science, Instruments and Paradoxes. Our understanding of cosmic limitations continues to evolve with new instruments, observations, and theoretical frameworks. Each advance refines our knowledge, sometimes confirming established limits, sometimes revealing unexpected complexities. Let's explore how emerging science shapes our understanding of intergalactic impossibility. The James Webb Space Telescope, JWST, launched in December 2021, represents a quantum leap in our ability to observe distant galaxies. With its infrared capabilities and unprecedented sensitivity, it peers farther into cosmic history than any previous instrument. Revealing galaxies as they appeared billions of years ago, these observations don't challenge the impossibility of intergalactic travel, but they deepen our understanding of galactic evolution. They reveal how galaxies form, interact, and change over cosmic time. They provide context for our own galactic home and its future. Webb's observations have already yielded surprises. Fully formed galaxies appearing earlier in cosmic history than models predicted, star formation rates that challenge existing theories. These discoveries remind us that while fundamental physics remains robust, our cosmic understanding continues to evolve. Ground-based astronomy advances in parallel with space telescopes. The Extremely Large Telescope, ELT, under construction in Chile, will feature a 39-meter primary mirror. When operational in the late 2020s, it will collect 13 times more light than any existing optical telescope. This unprecedented light-gathering capacity will allow astronomers to study distant galaxies in greater detail than ever before, to analyze their composition, dynamics, and structure, to observe not just their existence, but their nature, deepening our observational relationship with what we cannot physically reach. New detection methods are revolutionizing astronomy beyond traditional light-based observation. Gravitational wave astronomy, inaugurated with the 2015 detection of merging black holes, provides an entirely new sensing modality. Detecting ripples in space-time itself rather than electromagnetic radiation, these gravitational waves travel unimpeded through the universe, carrying information about cosmic cataclysms like black hole mergers and neutron-star collisions, events often obscured in traditional astronomy, opening new windows onto previously invisible cosmic processes. Neutrino astronomy represents another emerging observational frontier. These nearly massless particles interact so weakly with normal matter that they pass through entire planets unimpeded. This same property makes them extraordinarily difficult to detect, requiring massive underground detectors. Yet neutrinos carry unique information from cosmic sources, including supernovae, active galactic nuclei, and potentially the early universe itself. They tell stories that light cannot. They reveal processes hidden from traditional observation. They expand our cosmic perspective. Multi-messenger astronomy, combining observations across different detection methods, provides the most comprehensive view of cosmic phenomena. Light, gravitational waves, neutrinos, and cosmic rays each tell part of the story. Together they create a more complete cosmic narrative. These observational advances don't alter the fundamental limitations of intergalactic travel, but they transform our relationship with the unreachable. They allow us to know what we cannot touch, to study what we cannot visit, to establish meaningful connection across unbridgeable distances. New theoretical frameworks similarly reshape our understanding without overcoming fundamental limitations. Quantum gravity theories attempt to reconcile general relativity with quantum mechanics. String theory proposes additional dimensions beyond the familiar four of spacetime. Loop quantum gravity suggests spacetime itself emerges from more fundamental quantum structures. These developing theoretical frameworks don't promise practical methods for intergalactic travel, but they deepen our understanding of spacetime's fundamental nature. They refine the very concepts of distance, time, and cosmic structure that define our limitations. Paradoxes emerge from these theoretical explorations. The black hole information paradox questions whether information that falls into a black hole is truly lost. The firewall paradox examines contradictions between general relativity and quantum field theory at black hole horizons. These unresolved questions mark the frontiers of our understanding. Such paradoxes don't suggest imminent breakthrough in intergalactic travel, but they remind us that our understanding remains incomplete, that established physical theories may require refinement at their intersection points, that conceptual surprises may await at the boundaries of current knowledge. Dark energy, the mysterious force accelerating cosmic expansion, presents another frontier of incomplete understanding. Discovered in 1998 through observations of distant supernovae, dark energy comprises roughly 68% of the universe's total energy content. Yet its fundamental nature remains unknown. Far from suggesting possibilities for intergalactic travel, dark energy reinforces its impossibility. By accelerating cosmic expansion, it ensures that galaxies beyond our local group will become increasingly unreachable over cosmic time. The expansion barrier grows more formidable, not less, as the universe ages. Cosmological simulations using supercomputers create increasingly detailed models of galactic evolution and cosmic structure. These simulations, running from shortly after the Big Bang through billions of years of evolution, reveal how gravity, dark matter, and dark energy shape the universe's large-scale structure. They show galaxies forming along filaments of dark matter, clustering into groups and superclusters. They illustrate how cosmic expansion gradually overcomes gravitational attraction beyond certain scales. They visualize the cosmic web that defines our universe's architecture, a structure we can model but not fully explore. Artificial intelligence and machine learning increasingly assist in analyzing the vast datasets generated by modern astronomical instruments. These computational tools identify patterns, anomalies, and correlations that might escape human notice. They extend our observational capabilities beyond human limitations. Yet even these computational advances don't alter the fundamental barriers to intergalactic travel. They enhance our understanding of cosmic structure and evolution. They refine our models and predictions, but they operate within the same physical framework that establishes our cosmic limitations. As we integrate these advances in observation, theory, and computation, our cosmic understanding becomes simultaneously more precise and more humble. We know more than ever about the universe's structure and evolution, yet we also more clearly understand the boundaries of what's physically possible. Perhaps the most profound insight emerging from these advances isn't about overcoming limitations, but about accepting and working within them. Not about transcending cosmic boundaries, but about exploring them with greater precision and clarity. Not about conquering distance, but about connecting across it. This perspective doesn't diminish human cosmic potential. It contextualizes it. It doesn't restrict our cosmic relationship. It refines it. It doesn't end our cosmic journey. It defines its pathways. Not through physical presence, but through observation, understanding, and appreciation. Chapter 10. The Big Reveal. As we approach the culmination of our journey, let's directly confront the central question. Why is it impossible to reach another galaxy? Not with speculation or wishful thinking, but with the clearest current understanding of cosmic reality. The answer lies in 4 interlocking barriers. The first and most fundamental barrier is distance. Our nearest major galactic neighbor, Andromeda, lies 2.5 million light-years away. Light, traveling at 186,000 miles per second, takes 2.5 million years to reach us from Andromeda, and most galaxies lie much farther. This distance alone would make intergalactic journeys challenging, but not necessarily impossible. If we could approach light speed, perhaps through generational ships or suspended animation. But this first barrier compounds with 3 others to create true impossibility. The second barrier is cosmic expansion. The universe is not static, but expanding. This expansion accelerates over time, driven by dark energy. Galaxies beyond our local group are not just distant, they're moving away from us at ever-increasing speeds. For galaxies beyond a certain distance, currently about 16 to 17 billion light-years, this recession exceeds light speed. Not because these galaxies move through space faster than light, which relativity forbids, but because space itself expands, carrying them away faster than light can travel toward us. This creates a cosmic horizon, a boundary beyond which objects recede faster than their light can reach us. Galaxies beyond this horizon are permanently unreachable, regardless of technology. We can see them as they were in the past, but can never reach them in the future. Even for galaxies within our cosmic horizon, expansion creates an ever-moving target. By the time a hypothetical spacecraft reached the former location of a distant galaxy, that galaxy would have moved much farther away. The destination recedes as we approach. The third barrier involves energy requirements. Accelerating any object with mass requires energy. The closer that object approaches light speed, the more energy is required. This relationship isn't linear, but exponential. The energy curve becomes increasingly steep, approaching light speed. Einstein's equations tell us that reaching exactly light speed for any object with mass would require infinite energy, a clear physical impossibility. While we might theoretically approach 99.9% or even 99.999% of light speed, even this would require energy beyond our technological capabilities. Consider the implications. The fastest human-made object, the Parker Solar Probe, travels at approximately 430,000 kilometers. This represents about 0.064% of light speed. Reaching even 10% of light speed would require orders of magnitude more energy than our entire civilization currently produces. The fourth barrier is time. Even if we could overcome distance, expansion, and energy barriers, intergalactic journeys would span millions or billions of years. Time frames that exceed not just individual human lifespans, but potentially the lifespan of our entire species. Human civilization has existed for roughly 10,000 years, our species for about 300,000 years. Even the dinosaurs existed for only about 165 million years. Intergalactic time frames dwarf these periods. They challenge our very concept of continuity and purpose. These four barriers, distance, expansion, energy, and time, interlock to create not just practical difficulty but true physical impossibility. Not a temporary technological limitation, but a fundamental constraint inherent in our universe's structure. A cosmic boundary as real as gravity itself. This is the harsh reality promised in our title. Not harsh in the sense of cruel or punishing, but in the sense of unyielding. Not a limitation we've imposed on ourselves, but one the universe has established. Not a boundary to be overcome, but one to be understood. Yet this understanding need not diminish us. Consider the perspective shift it invites. If the Milky Way represents our cosmic limit, then our focus naturally shifts from endless expansion to deep exploration, from breadth to depth, from conquest to comprehension. Our galactic home contains hundreds of billions of stars, countless planets, moons, asteroids, comets, nebulae, star clusters, black holes. A cosmic neighborhood so vast that even if we visited one star system per day, we couldn't see them all in a billion years. This reality invites us to develop deeper appreciation for what lies within reach, to explore our cosmic neighborhood with greater attention and care, to understand that limitations don't diminish meaning, they define it. Boundaries don't restrict significance, they create it. The impossibility of intergalactic travel reminds us that the universe operates on its own terms, not ours. That physical laws aren't suggestions but definitive properties of reality. That understanding these laws doesn't limit human potential. It directs it toward achievable wonders. This perspective also has practical implications for our cosmic priorities. If intergalactic travel remains forever beyond reach, then massive investment in theoretical, faster-than-light propulsion represents misallocated resources, efforts better directed toward achievable cosmic goals. These goals might include developing sustainable human presence throughout our solar system, establishing observational outposts at strategic cosmic locations, creating ever more powerful telescopes and detection systems to study distant galaxies we cannot reach, deepening rather than broadening our cosmic relationship. The harsh reality of intergalactic impossibility also carries evolutionary implications. If all intelligent species throughout the cosmos face similar limitations, if all are similarly confined to their home galaxies, then the universe consists of isolated islands of intelligence, each evolving independently. This might explain the Fermi paradox, the question of why, given cosmic vastness, we haven't encountered other civilizations. If all technological species are galactically bound, their absence from our galaxy becomes unsurprising. Their existence elsewhere becomes both likely and irrelevant to our direct experience. Perhaps most profoundly, accepting our cosmic limitations might foster greater appreciation for Earth itself. If our species remains forever bound to the Milky Way, then our home planet's significance increases rather than diminishes. It remains not just our origin, but our enduring foundation. This perspective might encourage greater planetary stewardship. If Earth represents not just our temporary cradle, but our permanent wellspring, its preservation becomes crucial. Not a launching pad to be abandoned, but a foundation to be protected and treasured. As we close this exploration of cosmic limitations, consider that accepting boundaries doesn't end our cosmic journey. It defines its nature. It doesn't diminish cosmic wonder. It contextualizes it. It doesn't restrict human potential. It focuses it on what lies within reach. The Milky Way alone offers more mystery, beauty, and discovery than we could exhaust in 1,000,000 years. More worlds than we could explore in 1,000,000,000. More wonder than we could comprehend in 1,000,000,000,000. Our cosmic home provides near infinite possibility within finite boundaries. As you drift towards sleep, consider the paradoxical comfort in cosmic limitation, the clarity that comes from knowing our boundaries, the freedom that emerges from accepting what we cannot change, the wonder that deepens when focused within reachable horizons. We began this journey examining why intergalactic travel remains impossible. We've explored the physics, the distances, the energy requirements, and the time frames that create this impossibility. We've confronted the harsh reality of cosmic limitations, yet perhaps the most profound discovery isn't about what we cannot reach, but about what we can appreciate. Not about destinations forever beyond our grasp, but about the journey available within our cosmic neighborhood. Not about transcending boundaries, but about finding meaning within them. The universe reveals itself not as an infinite playground awaiting human expansion, but as a precisely structured reality with definite properties. Not a space to be conquered, but a context to be understood. Not a blank canvas for human ambition, but a complex tapestry in which we occupy a defined place. Perhaps in this understanding lies a deeper kind of cosmic connection. Not through physical presence, but through knowledge. Not through visitation, but through observation. Not through conquest, but through comprehension. A relationship based not on reaching, but on seeing. As you continue your own journey through this vast, complex universe, remember that limitations need not diminish wonder, that boundaries need not restrict meaning, that accepting cosmic reality doesn't end exploration, but focuses it on what truly matters. Join us next time as we explore another cosmic mystery together.